The new section today is 7.4, so 7.4, creating scale drawings and scale models. So creating scale drawings and scale models. And just want to make a couple comments first. I wouldn't frantically write these down, but one, our Earth is round. It's a sphere, technically. It's this ball-shaped object. It's a little bit wider at the equators, and it is tall. But if you try to take that ball shape and put it onto a flat piece of paper, it ends up causing distortions. That's kind of one comment. Just kind of store that in the back of your mind. Second, mapping smaller sections of the Earth can be done well. So if you're not looking at the whole Earth, you're looking at like Michigan. Yeah, Michigan's a little bit curved on the surface of the Earth, but it's going to work out okay. So that's one. All right, now jumping into the notes, I want to actually go back and review real fast something that we did in section 2. And that we said for that, when you're looking at the scale of something, the way you could view that is though it's the new length that you want divided by the original. And our book, instead of that, actually says it's the scale length divided by actual length, but I think new divided by original seems to work a little bit better for most people. Now for me, when I calculate it, I like using this thing here. Maybe I'll put the square around the whole bit. I like using this fraction when I calculate it, but for me it's easier when I come up with a unit ratio or a unit rate for that. I like seeing it written out this way. And we always did the numerator and then the colon and then the original, the denominator. So as we go through and do some examples, you're going to see me, first of all, using this fraction to kind of change it to a unit rate or unit ratio. And then I like converting it over to this because this makes more sense to me as I actually think about the problem and making something bigger or smaller. All right, moving on from there. So I'm going to jump into the first example. And that's going to be, we're going to start out by making something larger. So I'm going to say I'm enlarging a 12 centimeter by 18 centimeter map on a 51 centimeter by 81 centimeter poster. And my question is going to be, what's the largest possible scale? So it's the largest possible scale. And when we have that, first of all, you could double it, and you'd end up with, instead of 12 by 18, you'd end up with 24 by 36. But we're saying, okay, what's going to be the biggest? What's going to be the biggest that would fill up this as much as you can? Sometimes it'll work out that, say, tripling it is going to fit perfectly in both directions. But usually, you kind of end up, if you triple it in one direction, it's maybe going to be a little bit too big in the other direction, so you couldn't quite triple it. And that's kind of what we're looking at today, kind of that problem. And I'm going to break this up really into two problems. I'm going to say, all right, I have my 12 centimeters and my 51 centimeters. What's the scale change that I can do for that? And once I'm done with that, I'm going to do the same thing for 18 centimeters and 81 centimeters. What's the scale change there? And then we'll see which scale change do we keep. So I'm going to go and use my equation there, my new divided by the original. And I'm going to start out with the blues. So my new size is going to be the 51. I want to take and make this thing, rewrite my equation. New divided by the original. Do it that way. So my new size is going to be 51 centimeters divided by 12 centimeters. And for that, that's going to be a lot more helpful if we change that to a unit rate. So I do 51 divided by 12, and I end up with 4.25. And so that's the same as 4.25 divided by 1. And I mistakenly said unit rate. We really have a unit ratio now because I have centimeters and centimeters. So we could actually include centimeters if we wanted to on both of those. Might be nice, but it's not really necessary because they're the same. So I'm just going to write it as though my scale change could be a 4.25 to 1. So if this is our width, 12 centimeters wide, making it now 51 centimeters wide, we can make it 4 1/4 times bigger. Now if I do that same thing but for my purples, my new height for my purple one is going to be 81 centimeters. The original height was 18 centimeters. So now if I were to change that to a unit ratio, I do 81 divided by 18, I get a 4.5. And now that's the same then as saying, okay, that's 4.5 over 1 because it's a unit ratio. So vertically, I can make this thing 4.5 times as big. So we have one blue here, what's our scale change for horizontal? We have a purple, what's our scale change for vertical? Question is, which one do we stick with? Well, if we were to go with the blue one we know is going to work perfectly for that width. The 12 centimeters that I have right here is going to change into 51 centimeters wide. My 18 centimeters that I started out with, because here I'm multiplying by 4.5, now I'm only multiplying by 4.25, it's not going to quite be 81. So that would fit on the page. If instead I went with my second ratio here, my second scale factor, of 4.5, we know the height of 18 changes into a height of 81. It works perfectly height-wise. But now, my 12 centimeters that I had width-wise, we know 4.25 gets me up to my maximum width. Now I'm multiplying, though, by this 4.5, which is going to make it bigger than 51. So what we just found is this doesn't work for the width. It's too big. And if you understand that, then you don't need to memorize anything. You can just think your way through it in the problems. But if you're more of a memorizer, here's what you could say. That when you're enlarging an object, so enlarging an object, keep the smaller difference. So keep the smaller. And if I lost you a little bit with, like, what in the world is the smaller difference? Well, if these are both centimeters. If you have 4.25 centimeters on a ruler and 1 centimeter on a ruler, looking at this thing here, that's going to be a difference of 3.25. Where if I were to get the difference here by subtracting, I end up with a 3.5. So you're kind of looking at the one number to the other number, subtract the large minus small, and you'll get what the difference is. So keep the smaller difference, because then it'll both fit. And my second example, I think this is a little tougher to reason through, but that might just be how my brain's wired. I want to draw a model. So I have a plane that's 12 feet by 66 feet. So a plane, it's 12 feet by 66 feet. Little apostrophes there for feet. I'm going to draw on an 8.5 inch by 11 inch paper. We want to make as big of a plane as we can and have it fit on the page. So what's the best scale? What's the best scale factor? All right, if we go back to our original equation then that we had at the beginning, it said that the scale factor is going to be the new size divided by the original, or the new colon original. And we need to look at it in both directions here. So I'll say, all right, my blue, I'm going to do this here. So my 12 feet is shorter than my 66. My 8.5 inches is smaller than my 11 inches. So the 12 feet and the 8.5 have to be lined up. So my new size, my new maximum size is going to be my 8.5 inches on the page. And I had 12 feet originally. Maybe I'll do like write in inches and feet this way. Now if you treat this like the one we did last, we do an 8.5 divided by 12. When we do this though, I wouldn't write this down. When you do that, you get to 0.708 with a bunch of 3's repeating after that. So you could, if you wanted to, go through, and again I wouldn't write this, you could say, all right, I have this many inches, this many feet, and you could say 0.708 inches equals 1 foot, and use that as your scale. I suppose technically there's nothing wrong with that, but that's often not the most helpful way to do it. Instead what they try to do is, as they set up a ratio or a rate like this here, that's really sloppy, but as they try to set this up, they try to never have a number like this that's less than 1. So there's a couple ways you could go through and do this one. One is that, well, essentially we want to have the 1 inch equals how many feet is kind of how we're changing it. So one way is to go through and kind of treat it this way. Well, I want to have a 1 inch. I just need to figure out, well, 1 inch is how many feet, so I have like x feet down here in the bottom. Then from there you could go back and cross multiply and divide like we did in previous chapters and say, okay, I have 8.5x, so 8.5 times x equals 12 times 1. So I did that times that equals this times this. And now I end up with 8.5x equals 12. Well, then from there, I want to divide both sides by 8.5. So if I do 12 divided by 8.5 in my calculator, I could say, all right, I'm going to write here, I'm going to divide by 8.5, show my work. Makes teachers happy. I come up with an x then is 1.41. In other words, my x value, this 1.41, I could put right there. So I have 1 inch equals 1.41. And just like my units right there are feet, my units here are going to be feet as well. So my scale now is going to be 1 inch. And because our units are different, we need to keep them in there, 1.41 feet. So this is going to be my scale change in one direction. And I want to take and erase this just so I can get my work a little bit closer together. Actually, I'm going to leave that in. I'm going to point something out. That's one way to get the answer. The other way is this. And this is a little bit shady math-wise. I hate to confuse you. What I did here is always going to work. So feel free to stick with that. But if you want to save some time, you'll notice what we really ended up doing is we had a 1 up here, and we're always going to have the 1, so that'll always be a 1. Multiplying by 1 doesn't do anything, so really this 1 right there, it doesn't really need to be there, so we could just kind of get rid of it. You'll notice then to find x, all I did to find x was I did 12 divided by 8.5. And so what you could do in this type of problem is just kind of do the division that way. If you do 12 divided by 8.5, that gives you the 1.41, and you could just write that below your 1 inch. And we'll do that with this next one instead of doing the cross multiplying and dividing. If I'm losing you and you feel like you're kind of making up math, feel free to not do it that way. I'd hate to mess you up. But if we're looking at this here, I have a 66-foot plane. I want to make that 11 inches on the paper. So my new size is going to be 11 inches. And my plane was 66 feet, so that's the original size. And if I want to take and change this into like a 1 inch over a certain number of feet, all right, to do that then, I could do my 66 divided by my 11, because that's where my 1 is going to end up, is in that 11 spot. And that gives me a 6. So I know that my scale in this direction is going to be each 1 inch is going to be 6 feet of my plane. So 1 inch on the paper is going to be 6 feet on the plane. So now for which scale do we use? In order to make it fit in this direction, I need to take 6 feet of it and shrink it all the way down to 1 inch. That's more shrinking than this. The difference is much bigger here. Because here I only have like 1.5 feet shrinking down to 1 inch. So this is going to end up being like 4 times, a little bit more than 4 times as much shrinking. So this here is going to shrink it down just enough to match in one direction, but it's more shrinking than this. So what we're finding is that 12-foot width is going to be shrunk down more than it needs to be to fit in the 8.5 inches wide paper. So 12 foot shrunk more than it needs for the 8.5 inches wide paper, but it'll at least still fit. If instead we'd taken every 1.4 feet and made it 1 inch, then when I get this 66 feet, if I'm dividing that by 1.41, it's going to be way bigger than 11 inches. So there's no way it would fit lengthwise. So if I lost you there, I guess you could listen to it again. You could try to think through it on your own, or you could just memorize this here. When shrinking an object, because we were taking this large plane, we're trying to make it fit on a piece of paper, keep the larger difference. Because that larger difference is going to be how much you need to make it fit in one direction, but it'll be more shrinking than you need for the other. But if you had kept the smaller difference, then it wouldn't be enough shrinking to make it fit in both directions. And again, the difference, you're really subtracting the two numbers. So this one here, the difference there is going to just be 0.41 when I do my 1.41 minus my 1. The difference here is going to end up being a 5 once I do the 6 minus the 1. That's it for this section.